Okay, that's perfect. So before we start, just to let you know, this call will be recorded. And during the presentation, you can share your questions in the chat box, and after that, we will address them. I am happy to welcome Professor Steve Eichhorn for today's talk, which will be about spinning a yarn, 30 years of spinning high-performance cellulose fibers. I would like to ask all the participants to please mute yourself, just to have a webinar in a better way. So to give you an idea of today's talk, the talk will cover the spinning of cellulose fibers from solvent processes using dry jet wet spinning to electro spinning. And to introduce our speaker, Professor Steve Eichhorn graduated with a bachelor degree in physics from University of Leeds in 1993. He then went on to do a master's degree and PhD at the University of Manchester Institute of Science and Technology in the paper science department. Following that, he carried out postdoctoral research under the supervision of Professor Bob Young in the Department of Materials Science and Engineering. After that, he was hired as a new lecturer in 2002 in the same department, which then became the School of Materials in 2004 when UMIST merged with the Victoria University of Manchester. He was then promoted to senior lecturer and reader, and then went to become chair of material science at the University of Exeter in 2011. At that place, he built an activity around sustainable material research and also took on leadership roles as a co-director of EPSRC funded doctoral training center, and he was the head of engineering. In September 2017, he moved to University of Bristol and into the newly formed Bristol Composite Institute and was interim head of school in 2020. He was then awarded the Medal and Prize in 2012 from the Institute of Materials, Minerals and Mining for his contributions to the material science, and the prize from Japanese Cellulose Society in 2017. He is also a chair of ACS Cellulose and Renewable Materials Division. In 2025, he was elected as a Fellow of American Chemical Society, the first UK-based scientist to be elected to the position. He was also elected as a Fellow of Royal Academy of Engineering in the same year. At the moment, Steve, I know that you are moving to Manchester to take up a new position as a director of Henry Royce Institute in November this year, if I'm not wrong. And that's a very quite impressive bio, and it shows the dedication of your work to the sector. So I think we have the presentation for 40 minutes. You can start whenever you are okay, and then I mute myself as well.
Okay, thank you very much for that kind introduction, and thank you to everyone who's attending this talk. So yeah, the title of my talk is Spinning a Yarn, 30 Years of Spinning High Performance Cellulose Fibres. I chose to talk about this because it goes right back to the roots of where I started, really, in terms of my PhD research, actually my master's research as well. So more than 30 years ago, in fact. So if I just tell you a little bit about the research in my group. So I carry out a lot of research into cellulose and cellulosic materials, and we cover different areas. We look at natural fiber composites. We've looked at nanocellulose composites. We do some work on water purification. We've spent a lot of time thinking about how to modify nanocelluloses for functional properties. We've done some work on energy storage, and we also work on bulk materials like wood, and so, you know, we cover the sort of whole range really, but all focused on cellulose. Now, where does cellulose come from? Well, those of you who work in cellulose probably don't need to know this, but you'll have all at some point come across this equation here. Carbon dioxide plus water gives you glucose plus oxygen. It's the photosynthesis equation, and it's this glucose here that's polymerized by the plants into long chains of cellulose. So these groups come together, they're polymerized by condensation polymerization, it's believed, and then you get long chains of these monomer units that form the sort of plant tissue along with other components. And of course, that's something that plants do, trees especially. And these are just some pictures of trees throughout all the seasons. Obviously, some growth sometimes of the season the growth is much faster than other types. So in the winter, you see a lot of dieback of woody tissue. But these are just some pictures that I've taken over different seasons of different trees. Now, when you take cellulose and you treat it with a chemical, you change its nature. And one of the very earliest ways of doing this was to actually dissolve the material. And so people looked at dissolution in nitric acid and other solvents way back in the 19th century, and those sorts of dissolution processes produce what's called regenerated cellulose. Now, it's actually quite difficult to dissolve cellulose, but nevertheless, in the early part of the 19th century, this became possible. And then people started to think, well, when you've done that, you can process it maybe into other forms, maybe into fibres. And this sort of really started with Joseph Swan, and he was taking a regenerated cellulose, a cellulose nitrate, and he was denitrating it using ammonium hydrosulfate to make lamp filaments, so to make fibres that would then be put into lamps. So he's sort of seen as the father, really, of regenerated cellulose fibres. Now, Swan came along and he tried to make fibres from this solution, but he failed to commercialise it. And he was trying to make what was thought of then as artificial silk. So people had seen silk and thought, well, that looks pretty nice fibre. Let's see if we can make this synthetically. Now, Chardonnay, French chemist, he displayed fibres and textiles from this route at the Paris exhibition, and he got financing to make Chardonnay silk. But around about a couple of years later, Cross, Bevan and Beadle, three British chemists who were working at Kew, they showed that wood cellulose would dissolve in a xanthate, cellulose xanthate, following treatment with alkaline carbon disulfide. And this is known as the viscose process, but they don't mention fibres at all in their patent. However, just a year later in France, there was a factory set up to produce the artificial silk, and that was using the nitrate process. Now, following a failed commercial venture in the UK, the new artificial silk company near Coventry went into liquidation, and that was based on the nitrate process. However, Courtauld in 1908 had been working for several years before that, and they produced the first fibre, viscose fibre, in 1908, and they made a profit from it. And Courtauld in the 1970s realized that they needed to produce fibres from other sources, as in they needed different solvents, because the viscose process uses pretty horrible solvents, and that led to what's called the lyocell process. Now, there is history after the 1970s, because Courtauld famously tried to expand their business very rapidly into the lyocell process, but they expanded too quickly and they bankrupted the whole company and actually went out of business and had to sell out in the end to Lenzing, who now produce lyocell. So this is these are the three people who are involved in developing this viscose process. But in terms of the fibres, you take some wood pulp, you treat it with sodium hydroxide, okay, and this makes an alkali cellulose, and then with some carbon disulfide you make the xanthate, and then you add some more sodium hydroxide and you make this viscose solution. Then you spin that solution through a sulfuric acid bath, through a wet spinning process, and you draw it, you dry it down, and then you bale it. And these are some very old fibres here. This is some viscose fibre that from the 1950s that I have in my office, and this is some rami actually. I show this because both these came in these jars, and unfortunately the jar that this came in smashed, which was very unfortunate, but never mind. This is a a picture of a fibre spinning process from a patent, an early patent on fibre spinning viscose. Now, what are the issues with viscose? Well, this is the Barat rayon viscose plant in Indonesia, and it's a source of a lot of pollution, a lot of environmental problems because of the location of this plant on the river here. But viscose still accounts for 90% of the world's regenerated cellulose production, but it uses toxic solvents. But cellulose is actually hard to dissolve unless you do use a toxic solvent, typically, particularly if you're using a solvent that you require the modification of cellulose first. Now, synthetic fibres, are not all to everyone's liking, and people do prefer a more natural feel to fabrics. And cotton is actually the preferred natural fibre for clothing, but cotton has its own environmental issues. So this is the global market share of fibres, and you can see the vast majority of fibres produced in the world at the moment are synthetics derived from oil. Then you have cotton coming next. Viscose is only 7%, other natural fibres 5%, and then you've got wool tucked in right here at 1%. So actually, in terms of regenerated cellulose fibres, the viscose process is still the dominant process. However, there are some niche areas where lyocell is used. It has a very similar processing route to viscose, except they use this N-methylmorpholine N-oxide solvent. Is a non-derivatizing solvent. That means you don't have to modify the cellulose in order to get the cellulose to dissolve. And this was the subject of my master's and PhD research on the fibres produced by that. And it was developed by Courtaulds, which was eventually sold to Lenzing, and they still produce the fibre now. Now, of course, cellulose processing doesn't come without some risk, and one of the big risks with the lyocell process is the solvent itself can undergo autocatalytic decomposition, which can lead to an explosion. And actually this did actually happen in 2003, and the incident involved a fire and explosion. It caused about £6 million worth of damage, €6 million in damage. But there are other explosions that can occur when cellulose is involved, and wood flower is a typical example. And here is a wood flower plant that's just been blown to smithereens. Actually, 4 people died during this wood flower mill explosion. If you create a lot of dust in a factory, that can auto ignite, and then it can cause a huge problem in terms of fire. This is actually a microcrystalline cellulose factory explosion in Telangana in India. It caused 46 fatalities, and that was only last year, June of last year. So actually, cellulose is quite an unsafe material to work with, particularly when there's dust generated. Now, we worked on lyocell quite a bit in the past, and we did quite a lot of work. Some of my early PhD students way back 20 odd years ago, Kenny Kong here was producing some fibres from lyocell. He's spinning them himself actually, and drawing them at different rates during the production process. And when you do that, you can increase the mechanical properties quite significantly. So you can get a very high stiffness fibre here, whereas if you have a low draw ratio, you tend to get something like this with a high extension to failure, but actually a low stress at failure. And he also looked at the skin core orientation as well across the fibres. So we were able to show that the highest orientation is down here actually. We were able to show how the orientation of the crystallites along the fibre differs from skin to the core of the material. And you always get this sort of distribution of orientation across the fibres. Now, what does fibre orientation and crystalline order look like on a flat plate X-ray diffraction pattern? So this is Cordenka here, which is a high modulus fibre, and this is lyocell. And you can immediately see that the high modulus fibre has a much higher degree of order, because these are more spot-like, the reflections, less arcing here, and actually there's more intensity further out from the pattern. So actually that tends to show that there's a higher degree of crystalline order. Whereas here you can see these are much more arced, and actually the definition is not so great further out. So further out tells you about the short range order of the material, and so the longer range order is quite significant here with this material. Now, you don't just have to use the solvents I've already mentioned. There are other ways to dissolve cellulose, and one of the ways is to dissolve it in an ionic liquid. Now, what is an ionic liquid? Well, sodium chloride is an ionic solid, okay, and its density decreases as the free volumes increase. So is introduced. So, you know, sodium chloride gets a 15% decrease in density as you sort of break it down. And the long range order breaks down. You get ions that become mobile. But in order to do that, you have to melt it. And to melt it, you need a temperature of about 800 degrees C. So that's not really a usable ionic liquid. However, there are some ionic liquids that are liquid at room temperature. And here's some here. If you take a butyl methylamidazonium and a trifolate anion, you can get liquids of these cations and anions that are room temperature liquids, but they're ionic, so they have free ions in there, and these ions are capable then of disrupting interactions in the cellulose, primarily the hydrogen bonding, to break the cellulose down. Now, one of the very early papers on dissolving cellulose in an ionic liquid was by Robin Rogers' group. Actually, they spelt cellulose wrong in the title, but it's nevertheless, it was a very key paper in the whole history of this. Now, we spun cellulose fibres from ionic liquids. So if you take microcrystalline cellulose in this case, and you dissolve it in an methylamidazolium diethyl phosphate ionic liquid with a co-solvent of DMSO, you can form liquid crystalline solutions. You get high enough concentration of the cellulose in order that it will form an anisotropic solution. And by forming an anisotropic solution, you can get a higher degree of orientation. Therefore, you can produce fibers with really high stiffnesses, over 40 gigapascals, which is pretty high for the cellulose, regenerated cellulose fibers. Now, we published quite a few papers on this. We were able to show how it's possible that these fibers can compete with e-glass, given the density of them. There is actually a commercial production of ionic liquid spun fibers, Ion Cell, which was developed by this guy here, Herbert Sixter. He won a big prize from the King of Sweden here, the Marcus Wallenberg Prize, which was it's a very prestigious prize that's given out by the same person that gives out the Nobel Prize. In fact, in the cellulose field, we tend to sort of see this prize as the cellulose Nobel Prize. So it's a really quite a spectacular event. I actually went to the event as well, so it was very nice to be there. But spinning fibers from ionic liquids is a thing now, and we've looked at all kinds of different ways in which to do this. As I say, the concept is that you might be able to replace glass fibers and use them in transportation and sport applications, particularly if you were able to turn them into carbon fibers afterwards. Now, dissolution is not always that simple, and it does depend on things called the Campbell-Taft parameters, where if you plot the net basicity, okay, and this beta value here, which is the hydrogen bond basicity. So I should say that sometimes that you can treat cellulose as acidic and sometimes as basic. Okay, it depends on whether you're using an acidic solvent or whether you're using a base form solvent. But there is, because of that dipolarity of the hydrogen, of the hydroxyl groups, it is possible to have a basic or an acidic dissolution mechanism. However, that said, if you plot all these data for the different ionic liquids here, and actually we're also looking at NMMO here as well, you'll see that NMMO just sort of fits in this window here where it's possible to dissolve cellulose, and just only these ionic liquids here are capable of dissolving cellulose, whereas the ones that lie outside the box do not dissolve cellulose. But sometimes it's not always necessary to dissolve. Sometimes you just want to modify the surface. So again, although you can dissolve cellulose using a certain number of ionic liquids, not all of them would be good enough to spin the fibre. So although you can get dissolution, sometimes the solution that you make is too viscous to spin. And so actually we looked at 17 synthesized ionic liquids here, 9 of which were novel. We used 6 to produce fibres, these 6 here. But you can see number 6 has an extremely high viscosity at a concentration that you might consider reasonable for spinning fibres, whereas number 1 has a particularly low one. So you can spin quite easily using number 1, but number 6 it's nigh on impossible to spin. It's the solution's more like treacle. Now, although you can spin fibres from some of these ionic liquids, they don't produce fibres of particularly high mechanical properties in this case. So actually, some of the ethyl methylimidazoleum systems that we were looking at were probably more applicable, probably more suitable for doing the fibre spinning. In fact, that's what we use now. We don't tend to use any other different. Well, we have a project with a company who produce a particular ionic liquid solvent system that we're using their system to look at filaments. Now, if you spin with a co-solvent, what it means is you could actually get additional solvent. You can get additional dissolution there. So you can push the dissolution further up in the sense that you'll be able to get more cellulose into the solution. And actually using DMSO as a co-solvent has its other advantages, because it is actually relatively low cost, it's low viscosity, and it's miscible within an ionic liquid. So we found that about 30% of DMSO with the solvent, with the ionic liquid solvent, was about right, and that sort of just pushed you up into the window, if you like, of net basicity. And so that's how we managed to achieve the high mechanical properties, is that actually we just, because of the DMSO, we're able to get more cellulose dissolved into the solution. And once you've got more cellulose dissolved into solution, that means you can get closer to the critical concentration required for liquid crystal formation. Now we have a program grant at the moment, which is being led by Imperial and ourselves, and Cambridge are working on this, and we're looking at research into bio-based materials. It's called the Valued program. It runs until 2028, and we're doing some fibre spinning at the moment here at Bristol. Now, often when you spin fibres, you typically have to undertake some purification of cellulose before spinning. You know, for instance, lyocell use a particular kind of dissolving pulp of a prescribed molecular weight. And actually, most solvents decrease the molecular weight of cellulose upon dissolution. Now, the use of cellulose to make a carbon fibre is also limited in terms of the retention of the carbon content. There's a theoretical limit to the retention of carbon with cellulose, but something like lignin has a much higher carbon content than cellulose. And so potentially you could make better carbon fibres if we can retain that carbon. So that's the concept of this particular project, and the postdoc Shinomzu, who's now left and is working in industry, was to actually see if we could just spin everything. If we could just take the lignocellulose straw that we get from the farmer who grows the plants. So this is a miscanthus fibre, and if we could just dissolve the whole lot into an ionic liquid, maybe we could spin fibres directly without the need to sort of fractionate the cellulose. And this is miscanthus here. This is it growing here. ESG Natural Capital it's a biomaterials company. They make compostable packaging, construction material, but they basically have a farm where they grow UK grass fibres. And they're experts on growing miscanthus. It's a perennial plant. It will grow really tall once it's established. It gives a very high return on biomass. It's currently used as a bioenergy crop, so they make it into pellets for biomass power generation. And it can store lots of carbon in the soil as well, so it's very good for the soil. And it's a low input crop. You don't require much fertilizer. very resilient, and we're exploring the use at the moment for the textile fibres. So can you dissolve the lignocellulose? Well, if you take a purified pulp, we used a eucalyptus pulp in this case because it's got lots of hemicellulose in it, and actually that's quite similar to the miscanthus in that sense. But actually the commercial cellulose pulp dissolves really, really well. However, our miscanthus only partially dissolves, and we end up with some fragments of fibre left. But we thought, well, hold on, why don't we just try and spin this as it is without worrying about completely dissolving the fibre? And that's exactly what we did. So these are the dopes that we produced. So the LCP 5 to 20 just refers to a 5, 10, 15 and 20 weight percent of addition of the lignocellulose pulp from the miscanthus. This is commercial cellulose pulp. This is the miscanthus here. So you can see that the viscosities and the shear rates, the viscosity with shear rate decreases as you increase the shear rate, which means that your solution basically shear thins. So that shows you that actually you could spin this material. And some of them, the zero shear viscosity, some of our solutions are, eminently spinnable, like LCP10, for instance. Obviously, as you go to higher concentrations, that zero shear viscosity increases quite considerably. This is a processing viscosity here that we calculated. It shows you that LCP10 is pretty reasonable, comparable to the commercial cellulose pulp, and you get sort of reasonable fibres from this. This is what the fibres look like. So this is commercial cellulose pulp. This looks very similar to very similar to many regenerated cellulose fibres. There's this fibrillar texture. You've got a nice circular cross section. However, when you use the miscanthus, you get some odd cross sections. They don't look as circular, and actually along the fibre length, it looks very rough. So you've got some undissolved fibres here. This is a smooth fibre surface of the commercial cellulose pulp. So actually you produced a sort of textured fibre. And what we think we've produced by doing this is a continuous natural fibre. It has a sort of natural fibre feel to it. These are some of the orientations of our fibres. So CCP, commercial cellulose pulp, you get a really high degree of orientation, whereas LCP 5, very low degree of orientation, LCP10, slightly higher, but still quite arced here across the meridian. So that suggests there's and we actually calculate in the paper the fibre orientation factor. So in terms of our mechanical properties, the stress strain curves look very similar to what you might see with many other regenerated cellulose fibres. But our moduli and strengths are down in this region here, mostly for the lignocellulose pulp fibres. This is commercial cellulose. You can actually get right up here, up to the sort of higher end of tensile modulus, but actually most of our materials are down here, which is not too dissimilar actually to a lot of other commercial regenerated cellulose fibres. If you compare them, some of the sort of lower modulus encoviscoses, and certainly lyocell even it can be quite low in terms of its stiffness. So what about future perspectives? Well, we've been doing some work at the Henry Royce Institute where we've been able to produce 25 meters of this fibre. So this is going backwards in the process. So the fibre's coming left to right, but I'm going backwards here, back to the spinning bath and the syringe. You have to allow quite a lot of slack on the fibre to not break the fibre, but nevertheless you can produce this fibre in a continuous manner. Here we go. This is the needle at the end here, just going into the bath. Okay, so it's a dry jet wet spinning, but we're using a syringe pump to pump out the dope. Now, in the early days of weaving cotton, and in Manchester, it was found that a caustic soda treatment, that's sodium hydroxide, aided the processing, and it's known as mercerization. It was developed by John Mercer. This is John here. So I've thought, well, what if we were to see ionic liquids not just as solvents, but also spinning aids to make continuous natural fibres? And there's something aesthetically pleasing about natural fibres, and people like the textures. So retaining that might have some benefit from a marketing perspective. Obviously, we'd have to explore all the dyeing properties, etc. But so that's a future subject. And we're currently using some of our fibres with an end user. Now, other forms of fibre spinning that we've looked at, one of which is electrospinning. Those of you who are familiar with electrospinning will know that when you apply a voltage to a needle here, a metal needle tip, and this contains some polymer solution, at the droplet at the end of the needle, the droplet gets deformed by the charge. Those charges accumulate as you increase the voltage, and eventually they repel each other so much to the extent they'll break down the surface tension of the liquid, and then you get this ejection of a polymer solution into a whipping instability, and you have a collector plate here which collects the fibres on the plate. Now, electrospinning was discovered in the early 20th century. Now, despite all the citations, it was actually this guy here, Rockcliffe Manley, a Canadian, Jamaican Canadian scientist, and his PhD student. They developed the technique for a polymer melt. And then Darrell Renneker came on and did a lot of work with polymer solutions. Now, melt electrospinning is less explored in the field. It's quite difficult to set up because you have to have a heating jacket around your syringe. But here we are. Here we have some stills, actually, of the forming meniscus at the end of the capillary, the Taylor cone, as it's called. And this is a single fibre here, which has of polyethylene, which has a shish kebab structure. Now, electrospinning of cellulose, of course, cellulose doesn't melt, but it does not easily dissolve in many solvents, and so actually it's quite hard to electrospin cellulose. People did try in the early days to spin cellulose using ionic liquids, but ionic liquids are non-volatile. They have a very low vapor pressure. So actually it's quite hard unless you add something into the solution with a higher vapor pressure. So something like DMSO is okay, but it's still not super great. So spinning cellulose directly is not that easy. However, if you take a cellulose derivative, like say cellulose acetate, that will readily dissolve in something like DMAC acetone. And then you've got a volatile solvent, which is one of the requirements for electrospinning. And then you can spin your fibers quite readily onto, in this case, onto a mandrel. So you get nice orientation here. Okay. And then we took our fibers after this and we deacetylated them to produce pure cellulose. So we took away the acetyl groups in a post-process modification. So then by taking those cellulose fibers, you can do all sorts of clever things with them. So we spun them with carbon nanotubes inside of them, then we deacetylated, and then we carbonized that material and made a carbon electrode, which was made a nice supercapacitor electrode, and we got some super properties from that. Libo Deng, one of my postdocs at the time. And then some later work, we spun fibers with a catalyst in, and we did in situ production of carbon nanotubes on the surface with a spun catalyst. But then later on, this isn't fiber related, but it just uses some material that was useful later, uses a piece of equipment that was useful later. Cynthia Adu developed this technique where she was taking some recovered cellulose nanofibers from pulp sludge and making them into aerogels, and she used this device here for making the aerogels. And then we subsequently used a similar device to make aerogels for batteries. So we managed to make some nice batteries. But then we used electrospinning here with some cellulose included inside it to make the separator between the battery electrodes. And here we were able to show that our cellulose reinforced battery separator was able to resist the puncture by dendrites. And you can see here some cartoons showing you how that was possible. We used polyether imide as a suspending polymer, and some cellulose nanocrystals were spun into that using the electrospinning process. We've also looked at water purification as well using electrospinning, and here we were looking at cellulose acetate recovered from cigarette filters, and we spun them into networks actually what we found is that our material, our recovered cigarette filter material, outperformed virgin cellulose acetate and certainly outperformed a commercial spill oil pad. So that was really quite nice in terms of its oil absorption capacity. We've also looked at composite toughening as well, so using something called an interleave, where you take a cellulose derivative spun network and incorporate that between the layers of a carbon fibre composite and use that as a toughening mechanism for the reduction of crack propagation. In this case, it's called a veil system. Okay, there's a review here that talks about veils. These are some of our fibres. They were actually cellulose acetate butyrate. We found that they increased significantly G2C, that's mode 2 fracture toughness. Got an increase in mode 2 fracture toughness, which was a good result in some ways. Mode 1 didn't seem to increase, so we sort of speculate in the paper as to why that might be. So thank you very much for everyone listening. This is just some of the group that have been working on the project. This is my group here at Bristol. I thank all the researchers and so on for all their help on this. We've had funding from EPSRC over the last few years. We're still funded by them, and thank you very much for listening. Oh, and from November, so this is the paper science building. In my introduction, they talked about the fact I did my master's and PhD in paper science. This is paper science at Manchester. It's due for demolition, actually. They're going to build something else here, but I'll be moving into this building, this new building here. It's the Henry Voice Institute. It's the UK's premier research institute for material science, and I'm going to be the director of the institute. I was announced earlier this year in June, so from November. Please do get in touch if you're interested in material science and want to get engaged with Royce. Thank you very much.
Thank you so much, Steve, for the presentation. Quite impressive. When we are talking about cellulose, it's kind of at the first sight, let's say it comes simple, but it's really interesting to see that you are kind of using that in different applications. The energy storage part is quite interesting for me as well, because I have the same experience in that area, and I think it's really nice to be able to use cellulose for those materials as well. Do we have any questions from the audience? Okay, in that case, I can start with my questions and then we'll get back to the audience as well. My first question is that, let's say, over the years, what has been the biggest breakthrough in cellulose fiber spinning that kind of most changed the field, in your opinion?
Oh, right. Well, from a commercial aspect, I think, you know, the ionic liquid spinning, I would think, I mean, that's not just, you know, that's not just been done by me, but I think it's pretty impressive to take that process and make it commercial and commercially viable. And I say that because it's not easy to introduce a new fiber into the market. So it's not just a scientific result. I mean, it required some science to do it. I mean, I didn't really mention all the issues that they had to overcome, but not least, you know, being able to recover the solvents as well, because actually the cost of ionic liquids is quite high, relatively high. But if you can recover the solvents and recycle it, then it becomes less of an issue, and that's what they were able to do. So, yeah. So I think that, for me, from a regenerated cellulose fibre point of view, I think that's probably the biggest leap forward, I would say. There have been lots of other solvent systems that have been looked at that have produced very impressive properties. So there's a phosphoric acid process that was developed by AkzoNobel, and that had loads of potential, but it never got commercialized fully. So
Okay, quite interesting. Yes, ionic liquids are kind of a very hot topic these days. And as you mentioned, yes, we know them for their high cost and the recovery challenge. How the industry, or let's say research centers, kind of progressed in that aspect for recovery of them. Do we have any good results, optimistic results
Yeah.
in that area?
Well, Ion Cell have managed to recover their salt. I mean, it's just, and then there's companies that. So I work with a company through the value grant that was set up by one of the professors, a couple of the professors on the grant, called Lixia. They use a solvent system. It's commercial. It's a commercial name. It's called Ion Solve. It's a low-cost ionic liquid solvent system. So, you know, people have done a lot of work on trying to make these things lower cost, but also recovering them as well. So I think yes, there've been lots of leaps forward in being able to recover ionic liquids.
Okay, that's really good. And then my other question is that, let's say when we want to translate whatever we are doing in the lab scale to industrial scale, what is the main challenge at the moment in the spinning area?
Well, I mean, if you're going to scale, and I think you should look at some of the things that went wrong before. So if you're going to scale, I mean, it's not even a science thing. You have to be sure that you're going to be able to sell the fibre, and it might sound obvious, but you know, viscose still accounts for nearly 90% of the world's production of regenerated cellulose. So, you know, introducing a new fibre into a market where there is an established fibre that sells, you know, really well. I mean, and nobody wants a new fibre. Okay, so unless you can justify a new fibre and there being a market there for a new fibre, and it's competitive, cheaper, I don't know, it the environmental potential is obviously good, but that will only ever get marketed. It's never going to be somebody's you know, people want to be able to make money. Yeah, at the end of
True.
the day. So whatever you know, people think about the environment, at the end of the day, this is business. So the margins on production are quite low. So being able to make enough fibre to make it commercially viable is key. So I would say that the challenges aren't even technical. I mean, we know that we can spin fibres at scale. That's not the problem. The problem is having a market.
Okay. And how do you think we can work around that? I mean,
No.
what steps should be taken kind of to have that market?
Well, I mean, that's a difficult question to answer because you're requiring on the changing of attitudes of people. I think, you know, having a fibre that appeals. I mean, this is an aesthetic, right? It's, you know, it's how it feels on you. It's how it. I'm just pulling my shirt. This is a cotton shirt here. I only really wear cotton shirts. I don't wear synthetic fibres. I don't like the feel of them. They make me itch, and for some people, that's, you know, that's a real problem. So yeah, so I think you know, before you set up a business, you have to be sure that your customer base is there and it's going to accept your fibre. So
Yes.
yeah, I mean, honestly, this doesn't sound very scientific. I mean, we know how to make fibres, spinnable fibres. You know, that's not a problem. It's really bringing new fibres into the market is very difficult.
Yes.
I've
No,
got
that
some
makes
questions
sense.
here. I've got a question online here. It's actually been
Yes.
put into the chat.
Are you able to see that, or I can
Yeah,
read
I
that
can
to you?
see that. Yeah.
Great.
So shall I start from the first question? So, Yolanta, hi everyone. It's great to be here. My name is Yolanta, Senior Business Consultant, Optimat. We support EU projects, exciting strategies for exploitation planning. big fan of fibrous materials. Okay, that's great. I will follow you on LinkedIn. Suzanne, you said, I wonder if there's a shared presentation one could see, or is it me having a problem seeing it? I hope you
Yeah,
got to see that, Suzanne.
yes, it's
Okay,
solved, I think.
solved. Okay. Rahul, you said, thank you for the wonderful presentation. Deep eutectic solvents are also considered as an alternative to ionic liquids. Have you worked in any deep? Yes, we have. So we've worked in with choline chloride, a deep eutectic solvent, and the big challenge that we found is it doesn't dissolve cellulose. In fact, it barely modifies it. So I think deep eutectic solvents can sometimes be a misnomer, as in they don't actually dissolve cellulose, particularly the most common ones. But what they can do is they can act cooperatively with another solvent. So there's been some work fairly recently on spinning fibres using deep eutectic solvents as a co-solvent with an ionic liquid. That does seem to have some benefits, I believe. So yes, we used, let me just, here we go. We published, if you're interested, we published, no, that's not, we published a paper, Understanding the Interactions of Cellulose Fibres and Deep Eutectic Solvents of Choline Chloride and Urea. So choline chloride and urea is one of the most common DESs, deep eutectic solvents out there. And yet we found, you know, with a number of different techniques, that it didn't really dissolve cellulose. Could the new fibres be used as a biodegradable yarn, and is it commercially available? My guess is yes, but it's not commercially available.
Okay,
We
thank you
haven't
so
made, we don't
much.
make enough of it to make it commercially available. So
Hopefully.
yeah, we'd have
Yeah,
to really scale it up to make it worthwhile.
yeah, no, that's true. I have a last question because these days everybody is talking about AI. And how do you see AI influencing the development of new fibers or even new process to make
Oh wow.
fibers?
Okay, yeah, that's a difficult one. Well, I mean, carbohydrates and sugars are deeply complex materials. I think so if you compare it to proteins, the number of different ways in which sugars can link to each other is infinitely more complex. The sort of regioselectivity, the glycosylation they call it of the sugars is infinitely more complex. So that gives you many more permutations of structures that you can actually achieve. So maybe AI has some role to play there in disentangling what the function of the different structures are. Whether you want to make fibers in that way, I don't know. I don't think that's probably a good way to make fibers, bottom up from sugars, because nature does it for us already. So, you know, it's much cheaper to do that. But if you are adding function to the fibers, then possibly augmenting the structure. Yeah, so I think AI probably has a role in synthesis, in bottom-up synthesis, but perhaps that's just for specific sugar types, you know, for interactions with cells and things like that. Maybe there's ways in which we can make bespoke sugars that will interact with cells in a particular way that we can coat onto the fibers, for instance.
Okay, that's interesting. And we have two more questions. Yes, so the first one is that what are the challenges in scaling up? And also if there is any option to make filaments from cellulose for additive manufacturing, like 3D printers?
Oh, right. So the first question. Yes. What are the challenges in scaling up? Well, I don't know because we haven't tried to scale it further than the 25 meters that we've done already. I suspect is being able to produce multi-filaments, because you normally would spin several filaments at once, and we've managed to produce use spin 18 filaments from our system here. But I think, being able to spin multiple filaments into a solvent bath and for them to all have the same properties, and there's so many different challenges, really. Yeah, and having the sort of, when you've got the COSOL, the DMSO, having that in a laboratory situation is fine, but having it in a big scale might be quite difficult. Yeah, and just making sure that the properties are regular, that you manage to keep the variability of the properties of the fibers from day to day as minimal as possible. Yeah, I think that's the issue of scale, and not just on a commercial side of things. One of the big issues with scaling is how big. How big do you go? How much do you produce? Because, like I say, Courtaulds tried to expand far too rapidly because they perceived the market was going to grow much more than it actually did. And then, of course, they'd spent all that money on plants. They just couldn't. Yeah.
Yeah.
They couldn't recoup the cost.
That makes sense. Okay. And then we have another question. I think we covered that already, but I will read that. Maybe you want to add another point. If you have any plans to scale up using ionic liquids.
Not further than where we've gone so far. So
Okay.
we do have plans to do some more trials at that level at the Henry Royce Institute, but not any further than that.
Okay, that's perfect. Do we have any other questions from the audience? Okay, I think no. So thank you so much, Steve, for your time and the presentation. And thank you so much, everybody, for joining this webinar. And I look forward to see you all in the future webinars. Have a very nice day.
Thank you very much.
Bye.
Thank you. Bye-bye. Bye.
Bye.